Welcome to the afternoon session. I'm very happy to introduce John Beverley, who will speak about logic for ontology.
Thank you so much for having me. I wish I could be there in person, but I suppose this is better than nothing. So I'll try to be engaging. Okay. I'm going to assume everybody can hear me until I hear otherwise. So, but yeah, John Beverley, assistant professor at the University of Buffalo, ontologist by trade and training, logician by disposition and habits. So, but I want to tell you about what we do at the University of Buffalo first to set up kind of a stage for how we implement logic and our formalisms, because it's kind of the crux of our craft, as it were. But I think it does need a little framing. I like to frame it around the things that keep me up at night. You know, I'm a little bit of a frightened person often. I'm motivated by fear, and one of the things I'm afraid of is the proliferation of like information silos, which are everywhere. You see them all the time. If you've ever been to a healthcare provider and had to relay your health information to them, despite the fact that, say, you're in the same hospital as a physician you'd already previously relayed this information to, you have encountered silos. Most of your life, you probably encounter information silos where data just cannot easily be moved or integrated with other data. It happens all the time. We learn to cope with it. It's one of the things that upsets me throughout my life. It's one of the things that I'm trying to address. It's one of the things we address when we deal with ontologies. Ontologies, though, just formally well-defined machine interpretable control vocabularies that represent entities and logical relationships among them. They're designed to help make explicit the implicit meanings buried in data that's federated or separated across different databases. Often, we like to speak in terms of metaphors despite trying to be precise. We try to provide a semantic layer that connects information silos. To do that, we need formalism. This field, these ideas rest on two pillars, I like to say. So interoperability, which is ways or strategies of addressing information silos, and then information quality, which is how do you use those previously stated strategies to improve the quality of your data or quality of your information. I'm going to take these each in turn because the important almost key feature of our discipline is that we try to address interoperability and information quality issues at the same time, which is not common out in the field, out in the commercial space, unfortunately. So, but I want to be clear. So just to get a beat on what I'm talking about when I say interoperability strategies, I'm not one to try to give you a definition for what that is. There are plenty of definitions. Too many definitions, one might say, for what interoperability is. I don't find them very useful, but what I do find useful is thinking about them in terms of success conditions and axes, and these three are the ones that come up: human-human interoperability, human-machine interoperability, machine-machine interoperability. And when I'm thinking about the first one here, this is us. This is you and me talking, trying to get consensus over the way we speak. You might use the word organization and mean the sort of thing that must have at least two members. I might mean by organization the sort of thing that over its life can have just one member. That may not be important, but at some point it might be. Being precise about what we're talking about when we're talking to one another, that's the human-human interoperability challenge. We see this with constructing vocabularies and definitions and standards, sometimes motivated by education, legislation, consensus building, etc. Here's an example: dictionary from the Department of Defense, now Department of War. But the underlying central conceit here, as you'll see throughout these interoperability axes, is right here in bold and red. Any two speakers of a given natural language share some underlying formal structure. It is the job of an ontology engineer, as I teach, to find that formal structure. And we see it across the axes: human-machine. What do I mean when I'm talking about interoperability there? It concerns capability of computational systems to interpret and act on human understandable descriptions of the world. This is how we take that consensus, the understanding, the dictionary terms, the definitions, and we encode them into machines, and do so hopefully accurately, so that machines can reason over them, infer new information. Implementations of ontologies or logical models or data models fall into this sort of camp. You see here's like a representation of that DoD dictionary represented in what's called a taxonomy, or at least a visualization of a taxonomy here on the right. Again, central theme. Any two heterogeneous information systems share some underlying formal structure. This goes the same for encodings. Any of the encodings, any of the heterogeneous encoding schemes share some formal structure, and we're trying to find it. You'll see this represented in different languages. Your favorite flavor, whether it be the web ontology language I'll talk about later, or first order logic, RDF-lib, which is a Python library that allows us to use the resource description framework, which again I'll talk about later, or Sparkle, which I know Dean is going to talk about later, so I won't. But encodings, ways to interact with data, again, heterogeneous, nevertheless formal structure in common. Last but not least, machine-machine. So this is another axis of interoperability. Independent computer systems exchanging, interpreting, processing data without human intervention, often using protocols or translation schemes, REST APIs and whatnot. Another axis of interoperability, one that we always try to keep in mind because you're going to be surprised by this. When you're dealing with ontology development, whether it be from people coming from the outside or even ontology engineers inside, it is very easy to get these axes conflated and make mistakes and evaluate different strategies poorly because you've conflated the axes. These were actually motivated by listening to a couple of talks from Chris Partridge. I know he's going to love this, where he was attacking my colleague over here, Barry Smith. And Barry Smith, if you know anything about Barry, he loves his definitions. Chris is more of a machine-machine complexity kind of thinker. He wants to know how exactly, what's the best structure for translating, for the machine to translate without human intervention across different databases. And Chris would say things like, I don't care what subject matter experts in a domain think. And Barry would say, I do care what subject matter experts in a domain think. Well, that's because they were concerned with different axes of interoperability. Barry was concerned with the human-human. Chris was concerned with the machine-machine. It's not uncommon to get these things conflated. So prefacing, I want to make that clear. Again, the theme though, any two heterogeneous information encodings or systems share some underlying formal structure. That is what makes them interoperability themes or axes. Now, other side of the pillars, right? Information quality. We do both at the same time when we're engaged in ontology engineering. But what is this? By this, I just mean the fitness of information for its intended use. We are aiming to improve the quality of data for its intended use. That's sometimes a challenging thing to do. It's interoperability, that is connecting data. It's often pursued without reflection on how information quality may or will be impacted in different applications. On the other hand, information quality is often pursued without reflection on how interoperability will be obtained. These things are often done separately, but too much emphasis on connecting data leads to ontology artifacts or just models that lack the rich axiomatization needed to leverage tools to improve data quality. On the other hand, too much emphasis on information or data quality results in information silos. This is one of the ways, if you're focusing on your specific domain, you're really getting the data right for a specific purpose or application. You're not thinking about kind of a big picture. How is your data going to connect with other data? You're just going to create a silo. And I'll put this out there. We'll see you again in a few months. It happens. People leave and then come back regularly. And how can I do that again this time for the last time? I want to emphasize this because there are large companies out there in the commercial space who are claiming to use ontologies. I know they're over here in the States pretty regularly. I know they're over there as well. Some of them just a lot of them, the big ones, kind of just stitch together data using Python scripts. This is a great way to solve interoperability problems. You're creating executable code that you can run applications on, but they do so at the risk of making information quality downstream very challenging. I'm not going to name any names of companies, but if you hit me up in the chat, I'm happy to information dump on those commercial companies that I take issue with. But the upshot, though, is you have to do both if you're going to do these well. And traditionally in our field, the field of ontology engineering, 25 years, most people have not. That's unfortunate, but we're trying to be better at it now, which is one of the reasons why I'm emphasizing it every opportunity I get. So forgive me for that, but it needs belaboring. Best practices is doing both interoperability and information quality problems at the same time with a tradecraft that hits them both. And for what it's worth, the tradecraft that we adopt, the tradecraft that we teach over at the University of Buffalo in our graduate program, involves using a top-level architecture, a top-level ontology, modularization. Now I know, again, if you hear anything about ontologies in your own life or anything out there, you're probably thinking top-level ontology, oh no. really philosophical. Oh, great. John's going to start talking about weird things. Not quite. This is just basic software engineering best practices. Software engineers modularize. Software engineers use a language to extend with libraries pretty regularly. It's not that odd. And it's a lot more common than you might think too. Here's some what we call foundry efforts that use top level ontologies as a foundation and agree on certain principles around which to build structures, ontologies. So these foundry efforts, the one you're seeing over here on the far left is Open Biological and Biomedical Foundry. It's one of the first foundry efforts. It was motivated by the gene ontology, which was itself motivated by the Human Genome Project back in 1998, massive amount of data. A lot of researchers sitting around going, hey, if we don't get clear on what we mean by our terms, we're going to be talking past each other. An ontology was formed, a very minimal, slim ontology that's become probably the best funded ontology that I know of out in the open space, the gene ontology. And around that, though, was a set of volunteers who came up with principles about how to build ontologies, which was pretty useful because otherwise people were just building them as they did, creating ontology silos. But in any event, to avoid that in various domains, different foundry efforts have emerged, like the one in the middle, the Industrial Ontologies Foundry was created not too long ago, and the one over here, that NSO stands for National Security Ontology Foundry. It is a foundry effort going on that Barry and I are pretty involved in within the US government. So, but again, you'll see common representations is one of the principles, scoping, being clear about what you're talking about when you're modeling, textual definitions, because we have to have that human aspect, and a common top level ontology. Now, the one that has been chosen, the one I will talk about, is the basic formal ontology. Barry Smith, philosopher here at the University of Buffalo, where I'm also professor, he's the inventor of it. He's the advocate of it. He's kind of the dog for it. It is, again, as I said, adopted by these foundry efforts as part of the best practices. And I do think you need it or something similar. Doesn't have to be BFO. But if you're going to do ontology engineering and address both interoperability and information quality issues, you're going to need something like this structure. Now, I'm going to talk about this one because it's very widely used. You see here, it's the ISO 21832 standard. It's been mandated across the DoD and the IC for use for all of their ontology efforts. That's the top left over here. This thing at the bottom is supposed to, I'm not sure if it's a big deal. People tell me in the government it's a big deal, so I just put it in there. Sometimes people are like, yay, sometimes people aren't. But it's standardized across different groups, and it's used in over 700 projects across the world. And by used, I mean extended from. It's a very high-level vocabulary. It's a reserved vocabulary you might think of, which you can kind of base and extend formally different representations of things in the world, whatever you so may be interested in. Again, hammering this down, because I don't want folks to get too concerned about there being a top-level ontology discussion right here. It really is analogous to just you picking a programming language. I mean, it's not exactly right because ontologies in themselves not executable, but the analogy, for what it's worth, I think holds pretty well. You could create code that allows you to interact with data frames or whatever, or you could just start with Python and import pandas and do that. You could create ontology elements that allow you to model artifacts or processes, or you could just start with basic formal ontology and import an extension. Software development best practices, so widely used, BFO, is because the design methodology, the implementation methodology over the course of many years is focused on addressing both interoperability and information quality challenges at the same time. It's how we operate. I won't go through the details of the methodology because I don't have too much time, and I got some interesting things at the end here I want to show you, but I do want to point this out. So we're very much not inclined as ontology engineers, I think, to like prescribe meanings for specific domains. That is sometimes a misunderstanding. We are here to formally describe representations of different domains. I talked to a subject matter expert, somebody who's a virologist. I'm not a virologist. I want to know all of the details about their domain, the consensus about their domain. I don't try to tell them viruses are alive or not, even though that's a contentious thing. It's fascinating philosophically to discuss. I just have them lay the debate out, and then I model the debate as carefully as I can so that I can present it to them, to the actual subject matter experts, and let them decide. I put them, I feel, on a better footing to argue with one another and realize when they're talking to each other and when they're not. And that is kind of what we're doing often, not prescribing, describing. So not trying to tell you how the world is. I'm trying to describe how we believe the world is and let you sort it out if you're a domain expert. And all of this, again, in the interest, interoperability, the things we know, information quality, improving, adding a logical or semantic layer on top of this data helps you uncover the things that you didn't know you knew, or that you know you didn't know, and maybe kind of squish that last quadrant there, that unknown or the unknown unknowns, into a smaller space, because we're never really going to address that entirely. But how do you do this? I hear you cry. No, I can't hear anything. But just suppose for the sake of argument, you're given the task of representing some domain. It's in the interest of using machines to answer important questions about it. You could just build a BFO model, right? Like, that's totally reasonable. I just showed you this screen. Of course, you know what a continuant is. Of course, you know what a process boundary is, right? Not quite. Let me expand a little bit, and hopefully you can see the kind of formality that goes on here. It's really, really, really about disambiguating information. The examples you're looking at on your screen, like, I play with data a lot. Before I was a professor, I worked at the Applied Physics Lab at Johns Hopkins. We were data heavy, right? I see these confusions all over the place. These are real examples. Type versus instance. The instance Algeria, the instance of the country, often confused with being country, like a class of things, like a collection. Information versus what it's about. An occupation code for pharmacist versus the actual pharmacist of which it might apply. Or even better, I see this one most often, a coordinate system confused with what the coordinate system is supposed to be about. That happens surprisingly often. Like, information versus what it's about, just to be clear, is probably the most confused or conflated ambiguity that I see in data. But even so, material versus immaterial things, a given river versus the site where the river used to flow. If you're an archaeologist trying to find where a river used to flow, you're not looking for the material things you can touch, the water, the river basin, or anything like that. You're looking for a site where it used to be, where all of those things used to be regularly. Similarly, process versus product. I like to tell a little joke here: ontology engineering versus ontologies, process versus product, because one's a process, the other's a product. But really, like baking of a cake versus the cake you bake. Again, see these ambiguities quite often in data. They are so obvious you will forget them, is the thing. Let me say that again. These ambiguities, the distinction, these things, when I'm saying them to you, I know you're getting it. I assume you're nodding your head and going, obviously these things are not the same, right? Like, it's so obvious, people will forget to include it in their data. They do often forget to incorporate these disambiguations into their data. The problem is, if you're feeding this data to a machine, it doesn't know. You have to be clear, or at least clearer. Type versus instance. Look at this: types of sodium chloride versus the instances, or at least the visualization of an instance that you're looking at right here. Information versus what it's about, the measurements of rate processes of dissolving of H2O, dissolving of sodium chloride in H2O versus the H2O and the sodium chloride itself. Material versus immaterial, where the beaker is, where the beaker was versus the beakers themselves. Process versus product, that rate that's being measured by and represented in information versus that information itself versus the result of that rate. Again, they're so obvious, but they're so often overlooked because of that. There is, in the architecture that we use, though, formal representations of everything I just said, and dependency chains, like formal dependency chains that connects these things together so that machines can kind of trace through a structure like the one you're looking at. A process has a realization, some realizable entity that adheres in some material entity. I know that's complicated. Like, what is all this jargon? But a process like dissolving has a realization, which is the realization of what we would call a realizable entity in this case, which is solubility. Solubility adheres in, we say, some material entity, which is a sodium chloride. So you'll need at least those three things. You need a sodium chloride that's soluble. It may or may not ever manifest solubility. It may or may not ever dissolve, but when it's in context of unsaturated water, it does. And you have a dependency chain that runs through that, and you can represent all three, as well as logical relationships among them. Sites, I said, these are, and remember, I said sites are often confused with the material things that can be in them. It's like the river and the site where it was. Time, we also want to represent time, like when it was, all throughout the examples I was using. Processes going on, it had starts and stops and ends. That river used to flow, right? Also, we have dependency chains representing things like this. A material entity like salt could be located in a site. It also exists over time. At a certain time, there's some temporal interval in which it sits. Could exist all of it. And then, of course, we can have information about all of that. All information about the time, about the location, the material entity, information about the rate of solubility, information about when the realization occurred. You see, there's this, again, I just want to highlight relationships throughout the structure. It's not just a taxonomy. The temporal region is a occurrent, is an entity. That's just one flat version of the relationships. This is it's kind of a complex structure. And when I think of the relationships among these classes, I think of just formally relating different parts of taxonomies to different parts of taxonomies, and that's where you get a lot of logical power. Now, in practice, what we do when we go talk to subject matter experts is we don't have them we don't teach them what we're doing. We don't try to. I also don't want folks to go around, or my students to go around and try to have to think through all the logical dependencies very carefully, because formalism can be quite hard. We need like a path or a pattern or a recipe that allows us to kind of do this at scale. And so if you take an example like that, at what speed does a patrol boat move in knots and hours, or over an hour? This is a sort of question you might need to model for some subject matter expert in a given domain. If we're using the structure of BFO, this is protege representation. Protege is an ontology editor. It's one of our commonly used tool. It gives you a visualization of the taxonomy. On the left, you'll see the taxonomy of BFO. On the right, you'll see the taxonomy of relationships across the classes. So things like parthood, we've got the mereological relationships. Also, if you look here, we have has realization. So if you're thinking back to that dependency slide I had, it's a realization that's relating like the solubility and the dissolving together. We have a relationship specifically for that. And if you're taking like kind of a bird's eye view and trying to think of a recipe for how you would actually model speak English, man, BFO, or using BFO in this specific case, it's a 7-step process that's not that complicated. This is the sort of thing that I teach subject matter experts if they're interested, but students in an afternoon. It's literally just a 7-step process and you're good. You start with the things you can touch, the material things. Then you think about what kind of qualities they have. And I like to imagine, like, if you had to convey or describe the thing you could touch to somebody so that they could draw it, like a caricature artist or somebody like a police officer or something, you're trying to describe what this thing looks like, you would describe its qualities, its redness, its roundness, its shape, things of that sort. So you have the material thing, and then you have the qualities, things you might use to describe it. Then you have what those material things might do. It's the realizables, things like dissolve, things like be irascible if you're a somewhat angry person, or affable if you're a somewhat happy person. Things that not necessarily manifest all the time, but could manifest under certain conditions. And then you ask the question, what do these material things do? So, which is a separate question from what could they do, right? Salt could dissolve. Is the difference. And then you move on, number 5, to where is the stuff you're talking about located? Where are the material things? Where are they situated? When are they situated for 6? And then how do you talk about them? We save 7, information for last. And again, it's important. I said this earlier, but information is probably the most often confused class that we have. People often confuse information for what it's about, so we save it for last, because otherwise you will confuse it with one of the other 6. So again, just to reiterate, summarizing here, what can you touch? How would you describe it? What could it do? What does it do? Where is it? When is it? How do you describe it? That's basically the 7-step process for modeling things in BFO. I give you the example here. At what speed does a patrol boat move in knots over an hour? Hard thing. You can touch it. Skipped over qualities. This question that I'm asking, not really used, not really qualities. I mean, you could unpack or uncover qualities. You could think about its size and shape and whatnot. If you're answering the question, just sticking close to the question, maybe you have a time limit in a talk that you're giving and you don't have time to expand on it, this is probably what you want to do. So you can skip qualities, just go to a process, because it's moving, and moving is a process. Again, we talk about speed though. I put a question mark here on purpose because I said, remember, disambiguating. That's what we're trying to do. Speed is ambiguous. I think move is also ambiguous, but stay with me here. Speed, you could mean the measurement of speed, or you could mean the actual process of speed. Now, I say just note that, asterisk. We're going to come back to it, and you should note the ambiguity. We will come back, you always will, but note it and move on through the list because you want to fill out the list. Remember, it's a recipe, follow the steps. We'll come back to it, but if you don't do it, we'll get into arguments about what the ambiguity means, and we'll never finish the list. So my advice is always to move through the list, asterisk, we'll be back. Knots, measurement, like that seems like an information thing. It's a measurement. You have another ambiguity here, hours. Talking about a temporal region, or are you talking about the thing that, the information about a temporal region? Again, asterisk, move on. Disambiguating. Now we have to revisit. Let's revisit one at a time. Speed, process versus information about a process. You could mean by speed the magnitude of a change in position over time. That's something you might read out of a physics textbook. Information-y language. Or you could mean the changing of position over time, the thing that information-y speed is about, which would be a process. The question you should ask yourself when modeling, which do we care about when we're answering this question? We're always going to go back to the question, try to figure out what exactly we're trying to model. Now, for me, I always model both just because I'm a completionist, but still, if you're trying to answer the specific question, what were you trying to get at? Which of the ambiguities were you trying to resolve? Same for the hours. Time, are you talking about the time, the thing that information is about, or are you talking about like the interval itself, or the actual information itself? Ask the question. Now, once you've worked through this, and I made a couple of executive decisions here to drop some of these things off, you should simplify the list because humans have only so much bandwidth, so that you can focus on the smaller list itself, just the things you need to connect. You should then at this point, we just kind of use those relationships, that relationship taxonomy, to connect up whatever's left in the class structure that we just built. You got patrol boat, active motion, speed, hours, knots, measurement. And we do this by relying on 7 steps for the relations. Qualities are related to material things. Realizable entities like solubility that are related to material things. There's relationship there. Processes are related to material things, like the patrol boat moving. The process itself has a patrol boat as a material thing moving. Realizables to processes, like the solubilities has realization, the process of dissolving. Immaterial location of a material entity, we have located in for that. When things exist, we have existstat for that. And how any such entities relate to information about them is about. So you have like a taxonomy of connections across the classes. This is the point where we check out the list, we compare the list to see exactly which of these relations we need, we trim it down, and we revisit that class list that we had, or the instance list in this case. Patrol boats participate in processes, draw a connection. Same for speed, hours, knots, measurement. And this is how we proceduralize or try to recipe style the BFO modeling that we see. We get a question, we kind of trim it out with the taxonomies, the respective taxonomy that we have for classes, and then the respective taxonomy we have for object properties or relationships, as you're looking at here. And we just kind of draw connections as we work through the question, so that at the end of the day, we have a nice, pretty complex, somewhat complex picture, a logical structure of the question we had. Just like that, motion exists at some temporal region. Knots measurement is about some speed. So talked a lot about, so far, I think I'm doing pretty well on time, talked a lot about kind of best practices, how you operationalize seemingly complicated structures so that you can represent data and information, implicit information about the data that you might be encountering. But you might be wondering, as I would be at this point, how exactly this stuff gets encoded. And if you're tracking along the interoperability axes, you know where we are. So we use the semantic web stack. I've mentioned RDF at the beginning. This stands for Resource Description Framework. It's kind of the fundamental data model on which a lot of ontology development is conducted. I want to be clear here. It is often confused. RDF is often confused with a reserved vocabulary, which I will show you in a second. And the data model itself is confused with that. But when I'm talking about RDF right here, at least it's a data model. It just basically lays down structure or like a triple structure for the representation of encodings. Which provides semantics for distributed web data. Triple structure. Mary has a job executive. Subject, predicate, object. You can do this with multiple things. Subject, predicate, object, multiple relationships. This triple structure itself, you'll see encoded in what look like links, right? IRIs or URIs. We have a specific sort of link that, or specific sort of like structure that we use. But essentially, like if you're looking at like an encoding, you're going to see something that looks like in your web browser when you drop HTTPS in there. Uniform resource identifiers is what we call them. And you'll see the subject picking out one, hopefully uniquely, predicate picking out one, and object picking out one. There are serializations, different flavors that you might encounter if you're playing around with RDF. The simplest one is Terst, this Terst RDF triple language, because it just kind of highlights the structure that you're seeing here in a simple way. So Laurel is located in Maryland. That's a triple structure. You have up at the top with these little ampersand, a prefix. This allows us to abbreviate in the structure some parts of those link-like things, the URIs, so we don't have to look at all that nastiness. We can instead just kind of put a little notation in there. You'll see prefix EX colon. You'll look down, you'll see EX colon Laurel. If you take a gander right up in that oval on the left-hand side, you'll see the full thing spelled out. This helps us abbreviate it so we can see more clearly the actual triple structure. And you're looking, Laurel has a label, Laurel, and it's located in Maryland. In RDF, everything is expressed as a triple. Subject, predicates, and objects are names for entities represented as URIs. Objects may be literals, but subjects and predicates not. Literals are just like, labels, names, things like that, in quotes. That's as far as I'll go for literals right now. But the upshot is the subject and predicates have to be URIs. Objects may be like annotations. There is a reserved vocabulary, as I said, so don't confuse the data model itself with the vocabulary itself. I say it's confused because they have the same name and people often speak of them interchangeably, but they are separate. There's a lot of the vocabulary here. It kind of has somewhat sophisticated semantics, although kind of minimal. The one I would like to highlight here is type. It's a property. It's used to state that a resource is an instance of another resource, sort of. It actually doesn't really say that because, at least to my mind, to be able to say something is an instance of like a class, you have to have a reserved vocabulary term for class. And if you'll note here, there is not one, which is a good reason to think about a broader language that is extending RDF called RDFS. It's a schema language. It sits kind of on top. It expands its vocabulary and the data model that underwrites it to a more specific, more refined vocabulary that's actually more useful. So you have classes right here. Now you can talk about instances of specific classes. You can represent classes with RDFS. You can also represent subclass relationships. So we're kind of note what we're doing. We're building a formal vocabulary on this open source modeling. We can also talk about domains and ranges. So we have relationships. And we have they're always relating pairs of things. And we can talk about restrictions on the first element of the pair and restrictions on the second element of the pair. For example, if I want to create a relationship like has leaf, plausibly the domain will be plant and the range will be leaf, which is to say, anytime I use have leaf, I have a checker that says if you plug anything into the domain, like John, that's not a plant, you should get an error. We have sub-property relationships as well. So all of those relations I was showing you with BFO, the concretizes, has realization, parthood, etc. They are like related and they're pairing relationships that kind of transmit up a chain. So the upshot being here, if property A is a sub-property of property B, then any pair that you'll find in the set extension of property A will also be found in the set extension of property B. We also have data types. This is where we introduce some of the literal stuff where you can relate like classes or names or things or instances to integers or decimals or annotations. And there's a logic that underpins this as well, which just kind of sits outside of the semantic web stack, but is quite useful for it. You'll see integers, decimals, and whatnot there. Now, less interesting, I think, is what I just said, but it's all kind of building up to the web ontology language, which is, I think, where the logical power comes from. It's a lot of logical power. It's a family of vocabularies here. It extends RDF and RDFS. It creates semantics for constructing logical relationships among the resources. I'm going to focus here on OWL2. There's flavors. So there's a full version of OWL. I'm not going to talk about that one. That one is the kind of main difference you should take away from here is it's the full version of OWL extends outside of the decidable range. So OWL2 is decidable. If you ask it a question, it can a computing system a question using OWL2, you can be sure that you're going to get an answer one way or the other. A proposition, you're going to get a truth value one way or the other. That's not the case for OWL full. Some of the main differences, just one to highlight here, is that in OWL full, you are able to relate an instance directly to a class. You are not able to do in a way other than using typing, but you're not able to do that in OWL2. So for example, if you were marking data and you wanted to say, if you wanted to kind of be a little clear and say, I'm looking at an automobile, but I'm not sure what kind of automobile it is. I know it's not a tank. You can't really say using the the OWL2 structure that I know I'm not looking at anything from the class of tanks directly. That would be what you would need to do, or at least you would need to be able to relate that specific instance to a class itself. That's kind of off limits for here. So there are some limitations. Another notable limitation for OWL2, although this is or for OWL full, but also for OWL2, they're binary. The binary relations, you're kind of restricted to two. So if you want to say that John has an arm at a time and maybe doesn't have an arm at a later time, you're going to have to get kind of creative about how you represent that, because we have two place relations and we're kind of stuck with that if we're going to stay in this decidable framework. So clear relationship here, OWL2 to description logics, another family of logics, well-defined, like family of logics that are decidable. A lot of research going on over there. I want to focus mostly on how you would see this in ontology engineering practice rather than that formalism. Although if you're interested in my thoughts on OWL2, OWL full and all that, please go check out my YouTube channel. I have a lot of videos on this. I just want to kind of show you what these formalisms or this formalism looks like in practice when we're thinking about nothing, everything, union, etc., as well as complex combinations of these, because that'll be leading us up into the last portion of this talk. So if you open up a file that has OWL represented as an encoding, you're going to see representations of formalism that are logical relationships that you're familiar with, like nothing, the bottom, false, or top, everything. You're also going to see unions, just the connections of things. It determines the collections of classes they're just combining things, right? All the classes of deer, all the classes of students. The union is everything. Not necessarily together, but they're all together, not necessarily overlapping, that is, but they are together. Disjointness, of course, disjointness. The class of humans is disjoint from the class of plants, as far as I know, which is to say there's no instance in common across the classes. You can also create disjoint unions you can define classes that are just the collections of the collections of disjoint unions of other classes. My favorite example of this is the class country, which I see often defined. Country is a highly ambiguous term. Country, though, sometimes you can mean territory, sometimes you can mean people, sometimes you can mean government. It's not often the case that you mean all of those things. In fact, sometimes when I'm modeling data, stakeholders want to be able to live in the ambiguity. They don't want to be clear about what they mean. They do want to be clear about the fact that they never mean a territory and a government, or a people and a territory. But any instance they're referencing falls in one of those classes, but not in the intersection. So disjoint union is a great way to be able to model that sort of ambiguity, even in this kind of rigorous structure. Additionally, we can use identity or relating something to something else. I mean, these are very useful. I can say that two instances in OWL are the same. I can also say that anything that falls within a given class is related to something in another class. I can also say anything that's related to, I said this, I can also say that anything, any specific instance is not related to some other specific instance. So I gave you that example of not being able to say that this thing I'm looking at is not an instance of a class. Or I'm sorry, it's not a tank, that whole class. It's no instance of class or no instance of tank can be related to this. I can't exactly say that, but what I can do is I can pick out a specific instance of tank and I can relate this instance that I'm talking about and say it's not that. We got a question over here. 10 minutes left. Okay, good. Let me then, good, because I'm getting into the more interesting things. Okay, so hopefully I've given you the background needed because I want to talk about some issues or some like kind of important questions that come up in our field. So I was talking about basic formal ontologies, not the only way to represent things. They're bags of words, other ontologies, controlled vocabularies, thesauri, relational databases. We're often trying to map these structures into something like basic formal ontology. And we're doing so in kind of a rigorous way, formal way. And when I'm talking about mappings, which is what I'll be discussing here, I'm talking about kind of a formal foundation for code. So ontologies themselves are not executable, but I need when I'm thinking about connecting one representation to another representation, I'm not interested in creating a new ontology that combines them together. I'm interested in creating some kind of mapping rules or structure that I can write Python or Java on top of. And I want to be able to trace that. So it's got to be really careful, really formally specified. Else I'm going to have a problem downstream with interoperability. And so we have, if you're just sticking within the framework of something like OWL, you can lean on some of the representations they have, like equivalent class or equivalent property. When two classes are the same, you can say that explicitly, subclass of, subproperty of. And then you can talk about that rigor and like represent relationships across the structures, just in the way I was describing a moment ago. I'm going to give you an example here kind of quick because I do want to talk about the last thing even more. But if you're looking at basic formal ontology, it's kind of, this is from the protege viewer. You can see it's got some axioms, like logical axioms that define its structures. It's got like subclass relationships. It's got object property. That means relation in our speak. You can see some of them right here. So generically dependent continuant. This is like information-y stuff in BFO. It's disjoint from some of the other classes, which is to say they have no instances in common. Part-hood relationship, all instances of parts or of generically dependent continuant are related to only continuants, we say. They also have like logical relationships that govern some of the relations themselves. So some relations like a current part, this is a relationship between process-like things. It is transitive. So part-hood is transitive over that part of the domain. And we can assert these and they're logical axioms that represent the structure that I was just describing. And they're somewhat common patterns that you'll see if you dig into the formalism underpinning BFO. There's not that many. This is what it is. Like this is as complicated as the structure gets. You'll see right there. I will send these slides to you. You're welcome to peruse them or just ask me more details about them. But I'm highlighting this for a reason because if we compare it to other structures like the Information Exchange Standard, it's a kind of a top and mid-level ontology that's used over in the UK in their defense industry. Lots of axioms, lots of logical axioms, kind of a bigger ontology than what I was just describing. They have things like length and standard measure. They also have relationships like is part of with domain and range constraints. They have a few modeling differences for us, whereas we only allow for single chains of subclasses, subclass relationships being asserted. They allow for multiple or poly hierarchies, same for relationships. And they have quite a few domain and range restrictions as well. But really, ultimately, if you boil down their structure, this is what it looks like. This is as complicated as it gets. And when I'm thinking about mapping, I'm thinking about mapping structure to structure. And so I have things like this, the axiom patterns in mind. These are the axiom patterns in mind that I have when I'm looking across BFO and the IAS structure. This is kind of as much as I can get from them, which is unfortunate because I really want more than that if I'm going to map structure to structure in a way that's rigorous enough for executable. Now, there's a challenge here, which I don't have too much time to go through, but it does involve looking at their structure, adding axioms. If you're looking at this from the IAS perspective, which can be done step by step, just in the way I was describing earlier, and uncovering that background logic that which is implicit in something like that, which you're looking at. It's not too difficult, especially if you walk through the recipe list of the sort that I was describing earlier. But ultimately, you need that kind of mapping comparison if you're going to create something rigorous that you can write code on. This is the sort of line that I take to the IES people, and I say, I want to map to you, absolutely want to map to you, but you're going to have to give me more rigor if we can do this. And for what it's worth, they agree. So, and they're working on it. But the more interesting thing I want to talk about, the most interesting thing, is when we're talking about applications of specific ontologies. So I kind of give you a whirlwind here of some of the formalism, some of the semantic stacks, some of the use and why you would use ontologies. But you might be thinking, well, what happens if I'm trying to map some kind of structure into BFO that is not conformant to it? Maybe I need to do this for a specific application. Maybe I have a thesaurus that has some logical structure, some rigorous structure that is not aligned to BFO, and I actually need both. How do I do this? Well, let me show you. I don't tell me I don't have any more time. 5 minutes, perfect. That's great. Okay. Here's how you do it, guys. Okay. And hopefully this will be intuitive to everybody, but I keep having to beat this drum, so I'm just going to beat it again. So on the left, you're going to see BFO. This is a taxonomy of BFO. On the right, you're going to see a really bad taxonomic structure that I came up with just to illustrate that you can take garbage and interpret it in BFO as long as you track things well. So you'll see an operational area being a subclass of a ground vehicle. That should not be the case. A tank might be a subclass of a ground vehicle. It's not a great ontology over on the right-hand side. Here's how you can do this. Place the things over on the right where you think they should go in the BFO hierarchy. Just do that. Now, you've not solved anything. Like you've just kind of dropped in the BFO, or dropped in this bad taxonomy into the BFO taxonomy. Hold on, we're almost done. Introduce a new relationship. We'll call it military taxonomy. Make sure that this military taxonomy relationship is both reflexive and transitive. Why? Because that simulates subclass of relationships. And then assert that any instance, or the relationship, that any entity in the domain can be related only to instances under military artifact. And what do I mean? Like, use the only clause. You say military artifact taxonomy, this flight path, it relates only to aircraft. And why that specific relationship? Because that was the relationship that existed in the bad taxonomy. The flight path was a subclass of aircraft. Observe what I'm doing. I'm simulating the subclass of hierarchy within BFO. If you do this throughout, you can just push a button in an editor like an ontology editor like Protege. You can just push a button and have a reasoner infer the bad hierarchy within the scope of BFO. So again, they're not the same, but you have an inferred hierarchy that is precisely what you saw in the military taxonomy ontology, as bad as it was. Now, caveat, but an important one nonetheless, a caveat here is that to make this work, you have to drop some of the formal constraints within the class hierarchy of BFO. Sites and objects are disjoint in BFO. There's no instance in common. Operational area, because of this, cannot strictly speaking be an asserted subclass of object and infer subclass of site. That would be an inconsistency in BFO. Such constraints are fine in application. We don't have to be purists about the formal structure of BFO. This becomes a configuration management problem. As long as you can track what you had to give up to import or recreate a structure within the scope of BFO or any other ontology, that's fine for specific application. And I can tell you this actually came up from a specific application, which I can't really talk too much about, but it worked. It worked. As long as we were tracking what we had to give up, we could use tools and editors and reasoners to identify specifically the axioms we had to give up to make this work. Everything was fine. All the reasoning fine. In application, things worked out just fine. It just became kind of a software development issue that we had to deal with downstream, but we knew exactly where to look because we knew exactly what we had to give up. Summarizing. This discipline is focused on simultaneously addressing interoperability and information quality problems via disambiguation. To make good on these processes, we have to be careful, rigorous with our interpretations across structures, and we have to keep separate the semantics from the application or the operational layer. And with that, perfect. Let's talk.
Thank you very much.
Mm-hmm.
Any question? Maybe I will have a question. So you gave a nice example with this both examples of how you can decompose using this concept of BFO. So it gives you some sort of procedure on how to structure your ontology so that it integrates into BFO. But there's also the question of this is not straightforward, that when you start analyzing some sort of domain, there can be different way of doing things. And when you're working with expert, what happens often is that the expert know the field and he know how to explain the field, but it's quite often like what you will read in a text, or you will have some sort of narrative about the field, but it's not the complete story. It's like the big picture. And so you can start doing this kind of decomposition, but often you get stuck at some point because there's something that doesn't work properly, and then the expert changes his mind because he tells you, oh yeah, that was a big picture, but now in detail, this is not what you're having. But because it's logic based, then you're some sort of trap, because it must work down to every tiny detail so that it maps properly, and so that you can start the process. It worked out very well, and then you get trapped because you maybe as an ontologist, you have the impression that the expert is picking something new, but he will say, no, that was always in the narrative, but it was some sort of in the background that you have this. And so how does BFO help for that, or
I think so. I want to separate BFO
from
from the methodology. So I want to say I pitch this as a BFO methodology, but it is adaptable to any other structure. And so but what you're describing is very common. And so when I'm engaging with folks like subject matter experts, BFO aside, I get the questions from them that they're asking, like the patrol boat question. And then I ask them to unpack it with me, because as they start unpacking it with me, other questions come up. And I have them do that. And then they ask kind of sophisticated questions. They'll often ask sophisticated questions. And then what I'll do is, as they're kind of unpacking it, I kind of make them slow down and think about the details in the background. And then that gets them to think more about the details. My favorite example is a kind of scenario where you're modeling, like you have a blueprint for a jet, and the jet it's supposed to fly at a max velocity of like 100 miles per hour. That's 1,000 miles per hour. But then actual testing, 5 tests show you that the max it ever gets is like on average 980. So you ask a subject matter expert to like, how do you unpack what's going on here? And they get very far downstream very quickly. They start talking about like wind resistance and velocity, the terminal size, like where in the world you are. But as they're talking, you're like, that's important information. You write it down, but then back up and say, okay, how many processes are being measured? At least 5, right? And then you're taking an average of them. What is a specification or blueprint about? Is the blueprint the same sort of thing as the jet itself? No, right? And you start like kind of breaking that down for them, and then they start realizing there are questions that they have in the background that are like kind of percolating, and started uncovering and slowing down and building out the full model is a lot more intense than just that simple question on the surface level. And so that's my strategy. It's been somewhat successful, because I've often worried about getting too far in the weeds or too far in the details for exactly the reasons that you're describing. Like, I know as soon as I start asking questions, then more questions are going to come up. And we need to get to a steady state of questions where so much of the background has been fleshed out that there's really nothing left. And I do find a top level structure to give me the kind of like a grounding, so I know when to stop asking the questions. Like that 7 steps, like, tell me what else you would ask, right? If I have everything spelled out, what else would I be asking about? And so that helps me see that. And I think it helps them too, because again, unpacking the questions, but also working through the structure.
Yeah, but
Mhm.
inside that process of asking question, then
Mhm.
the setting can change quite dramatically.
Oh, yeah.
Because you have this you have this logical, formal, exact setting that you're trying to map the thing in, so that I mean, your strategy is good, but what surely happened is that it evolved a lot, at least at the beginning, before it stabilized to something.
Mhm. I do like, I mean, I found a lot of value in putting forward the as rigorous a structure to them as I can early on, because they have to fight it. I'm like, this is right. And then they see exactly like either what I'm saying or what I'm not saying. And that's what I'm aiming for. I want us to know exactly where we're talking past each other, and being as rigorous as I can at early on, as regularly as I can. That's how I get them to like really narrow down on what they mean. And that's really important because it avoids the ambiguities that come up in natural language. I mean, I'm sure you've talked to subject matter experts who get tired a few minutes into the conversation or start going off of habit and start memorize, like regurgitating something that they had memorized rotely or something they taught before. But you really want more of their attention, more directed, and so you kind of want to challenge them a little bit on their understanding by being rigorous yourself. We do have a question here from Kelly. So if you don't mind, so Kelly says, I'm completely lost. When you integrated the bad ontology in the BFO, you replicated the incoherent structure, but were you seeking to ultimately correct the initial framework and made it operationally correct? In BFO, it all went too fast for my brain. Not trying to correct them. So that's a bad ontology. I mean, I said that I don't think it was good, but unfortunately, it was a real example. It was like a confused structure, but it's not my job, at least early on, to say what structure is good and what structure is bad. I want to give a foundation on which they can like see themselves, or different representations can be interpreted. Now, after that exercise, after we see the kind of what needed to be given up, the difference between like the sites and and the disjointness that I had to drop, that is the sort of thing that I would bring to the people who created that structure and say, is this what you meant? And they may say, and it's only happened once, they may say, yes, that's exactly what we meant. We don't really buy into that difference that you're drawing on. That's fine. Again, it's happened one time where people are like, I don't agree with that division. More often than not, what happens is you bring to them the disagree, like that difference, and you point out what a site is and what the other thing is, and then you say, listen, did you mean to like run roughshod over this? And they'll usually say, actually, no, we needed to fix this. This happened somewhat recently in the open space with the GIST community. So the semantic arts community, they have GIST, this kind of ontology that's like business focused, business oriented. We've been working with them to create a mapping between BFO and GIST. And through that discussion, they were looking at the way we modeled and distinguished information from what it's about. And it turns out they had been kind of perplexed about the way they were modeling information for a few years. And so they saw what we were doing. They were like, actually, this is a preferable way. And so, but we got there not by going over and saying, hey guys, you don't understand how to model information. Never really trying to do that. It's more like, hey, here's how we're doing it. Here's how it would map in our structure. If we interpret what you're saying and how we're speaking, and you get what we're saying, then it's up to you on whether you change or not. So, Kelly, to answer your question, not at the initial stages. We want to kind of present and describe as carefully as we can what we're seeing, and then give that back to the researchers or give that back to the subject matter experts and let them make the decision on whether to change or not. They may want inconsistent, incoherent structures. They may not care about logic because they're doing something else in an application. It happens.
Question? Est-ce qu'il y a d'autres trucs en ligne? Non, non, ok. Rien. Oh, yes, there's a question.
Thank you for the presentation. Actually, I have a little bit technical question, because I have worked through the basic formal ontology that you introduced, and I found that there is an intermediate layer that belongs to the BFO ontology, which is the CCO, Common Core Ontology.
Mm-hmm.
It works with different, I call it like the intermediate layer after the basic formal ontology. My question is about, because I am working on something related to design a domain ontology. My domain ontology will belongs to two upper layers. The first layer is the BFO, which identify the common sense knowledge in general, very general concepts. Then we will go through the CCO, Common Core Ontology, and afterwards I will develop something I will call it Normative Core Ontology, and it will be a contribution and a specific domain knowledge. The question is, how do we determine the appropriate level of abstraction when modeling a domain, and how do we avoid creating ontologies that are either too general or too specific?
It's a great question. So you're talking to the right person. I'm the developer for CCO right now, the Common Core Ontologies as well. And so we are currently restructuring a lot of CCO because, as you probably notice, there's a lot of content in CCO that's we say it's a mid layer between BFO, a top layer, and then domains. But like that intermediate layer, there's a lot of stuff in there you probably don't think should be in an intermediate layer, probably should be kind of like lower down in the domains. Honestly, the reason that stuff is in there is because there hasn't been like principles around which to divide mid and domain level ontologies. And it was created by a lot of like specific use cases for stakeholders or sponsors in the government. They said, we need you to model this, go model this for the specific purpose. And then it kind of built things like Flywheel into the mid level. Now, where we draw the line, where we're drawing the line right now between CCO or Common Core Ontologies and then domains have to do with sort of broad structures that leverage significant portions of both CCO and the top level BFO based around design patterns that are pretty general themselves. So like modeling information, modeling artifacts at a high level and functions associated with them, things that could be realized like an automobile and its ability to like run over certain terrains or something like that. Like just kind of giving general structure that's more specific than BFO, but less specific than a given like ontology for Honda Civics or something like that. It's kind of where we're drawing the line right now. What this means is that a lot of the CCO content is actually going to be pushed down into lower domains. But it is motivated by kind of broad design questions or design principles that people in our community have been asking that cover a lot of what's in CCO. And by that, I mean like a lot of what sits under significant portions of BFO. I'm kind of saying this in hand wavy terms for a reason, though. There is no firm cutoff that anybody's ever been able to draw between a mid-level or intermediate level and a domain level. And that sounds like a cop-out, but if you think about it, there is no firm cutoff between BFO and a mid-level either. It's just that people don't have firm intuitions about time. They have firmer intuitions about automobiles. And so people kind of take more seriously what's happening closer to the domain than they did when Barry was advocating for like, this is where we cut it off. And so it's always been a heuristic matter. But again, the way we're trying to get through this is to say that for CCO, the Common Core Ontologies, what's going to stay in that suite of ontologies is going to be motivated by design patterns that are questions that need large portions of BFO and CCO to answer. And that's kind of going to be the rule of thumb to justify inclusion for classes and relationships in CCO. Everything else, things that are more domain specific, automobiles or whatnot, those are going to sit under. That's not to say that there aren't broad domains that sit under CCO that'll themselves have kind of large like intermediates below CCO and other domains. I mean, I created one, or like I developed one with Shane Babcock, this information or in infectious disease ontology, which has lots of little ontologies of infectious diseases that sit under it, but it itself sits under a broader mid-level ontology that sits itself under BFO. So I hope that answered some of your question. It is kind of a hand wavy answer, but unfortunately that is where we are. It's motivated by design principles, broad swaths of the classes and relationships that we need to use to model them. And that's kind of the heuristic that we have.
It will help her in her thesis, I'm sure. Thank you.
Say that again.
It will help her in her thesis, I'm sure.
Fantastic. And feel free to reach out. I'm happy to share, intuitions about where things cut off, or put you in connection with folks who have maybe firmer convictions about how to draw cutoffs than I do. So.
No other question? I think we'll thank speaker again. Thank you very much.
Thank you so much. Wish I was there.
Thank you.
All right.
Bye.